And hello, welcome everybody to this Labview. I'm gonna have some more discussion today. So, what are we gonna discuss today? Well, the last time we were talking about some of the interesting things with regards to making the frequency response fast Fourier transform. Okay, let me get the YouTube demo out. Yeah. And now I'll close this one. Yes. So this is our front panel and this is our block diagram. This is where we last left off. We were able to, for example, take a A note, which is about 110 Hertz, and then we are able to get the spectrum as such. And of course, we know now how to relate these frequency bins at the bottom here, and relate that to the actual frequency in Hertz for this sound file. And also know that if you type in 44100 here, which is the sampling frequency, okay, then your frequency bins are going to correspond directly to the actual frequency in Hertz that I was playing. In this case, an A note, which is about 110 Hertz, which you see this big peak over here. However, that only enables you to get the first 1 second, because that's 44.1 kilohertz and 44.1 thousand samples, and that's only gives the first second. If you want to analyze a very long waveform, you'll need to do some division. So like I was showing in the last video, you kind of just divide it by the time elapsed, or if you know what the sampling frequency is, you look at the FFT size, and then you find that the frequency, the amount of frequency that changes, the shift in frequency that changes between one frequency bin to the other frequency bin, that will be the number of the sampling rate, and you divide it by the total number of samples, or the FFT size, which is also equivalent to 1 over time in our case. Okay, so that's basically what we were doing. So you kind of have to do some manual work in order to make sure that the Fourier transform in general, the fast Fourier transform, corresponds directly to a frequency. So of course, it would be good if we can learn how to transform this fast Fourier transform into this power spectrum manually, okay, rather than just use this spectral measurement, because that will actually give you a bit more insight into all the nitty-gritty things that go in Labview, and of course that will actually get you started into how to deal with all these variables in Labview, such as arrays and even waveforms. So I want to start talking about arrays and waveforms, so that we can hopefully convert this fast Fourier transform, this raw data fast Fourier coming from the fast Fourier transform, into something like this power spectrum that you see here. At least we get some positive values, and we don't. Okay, let's see, I can scale it. Okay, so I'm going to scale my graph accordingly. So I'm going to go to properties, I'm going to go to plots, I'm going to go to frequency, and I'm going to type auto scale. Okay, when you have auto scale, you will go all the way from, I think, 0 to about 22,000 Hertz. Why is it 22,000? Remember that your fast Fourier transform, it has this mirror image, right? It has this mirror image. So if for example, I was doing 4,100 samples, 44,100 samples, okay, the left half corresponds to the positive part, the right half corresponds to the negative part. So if you have a sampling frequency of 44.1 kilohertz, the maximum frequency, the highest frequency you can sample up to, or you can detect using a Fourier transform, is actually your sampling frequency divided by 2. This is also called the Nyquist frequency. I don't know how to pronounce it, but I'll probably butcher the name, but okay, that's very important for you to know. The Nyquist, the Nyquist frequency. Okay, so this is the Nyquist frequency, which is the maximum frequency you can get, which is your sampling frequency divided by 2. Okay, I mean, I just quickly maybe spend about 30 seconds giving you some intuition why. Okay, so let's say you have your waveform like so, all right, and then this waveform takes 1 second, right? Your period's 1 second, so this is 1 Hertz. All right. Okay, so if your sampling frequency is 1 Hertz, what are you gonna get? Let's say you sample at this waveform, right? And then you wait 1 full period before you sample again. So what is your bar chart gonna look like? Your bar chart is gonna look like one flat line here, right? One flat line here. And if you keep going the same way, it's going to look like a flat line throughout. So what's the minimum kind of frequency you need to pick up all these waves? So what you need is, okay, the Nyquist frequency, that rule of thumb says you need at least 2 times the, if let's say this is 1 Hertz, that means you need 2 times that frequency, the sampling frequency, in order to try and roughly get the waveform. Okay, so if I have a sampling frequency now of 2 Hertz instead, okay, so I will sample have one sample here, then half a period later, which is 0.5 seconds later, I'll have a sample here, right? And half a period later, I'll have a sample here. So when we have such a case, you are able to at least make out that, okay, I roughly have a waveform there, okay, and your bar chart is going to look like this sort of a square wave. Okay, so it's going to go up and down like a square wave. So that's how your sampling will work. But you can see you need at least 2 times the frequency of the waveform in order to sample it properly. Anything less and it just doesn't quite work properly. You will not be able to distinguish a regular waveform from background noise. It's very hard to distinguish if it's your sampling frequency isn't high enough. So that's why I guess you can say that we can only sample up to 22.05 kilohertz. Anything more than that, you will not be able to sample because of that logic I just roughly gave you. So this is what the some intuition behind the Nyquist frequency. Okay, so of course, yeah, we want to move on. Discuss a little bit more about waveforms. Okay, so you see, what are waveforms? Okay, if you want to have the goal of getting the data from this fast Fourier transform and turning it into a power spectrum, and that's the goal. If that is the goal, then what you need to do is this. You probably need to learn how to deal with the arrays and variables that this fast Fourier transform is putting out. You need to understand what is being fed in and what is being fed out. So first thing first, we probably want to learn to deal with arrays and how to at least tidy up this block diagram. So first thing first, of course, I like things to be tidy. So how do you tidy up block diagrams? So you can right click this wire, and you go and click on the option saying clean up wire. Once you click on that, you see that the wires, they start to organize very nicely. Okay, it's looking much better if you just right click and click the clean up wire. Okay, and it'll look very much neater than what we had before. So all these crooked lines will be straightened. as far as possible, and that's basically the cleanup wire. What do you want to also do next? Okay, so if you see this dashed brown line, okay, these are so-called waveform data, right? What is a waveform data? Okay, so basically when you have your audio file, all right, basically when you have your audio file, okay, when you have your audio file and then you have, okay, I'm not going to draw all the bar charts here because it's really hard to draw. Okay, let's say you have this kind of a signal, right? So you have all these bar charts here, so-called bar chart looking like a graph, which is actually your frequency. I mean, it's your sampling. It's your sampling your digital, I think not quite digital, discrete time signal of your audio file. Okay, so they will have this sampling frequency interval, right? Okay, they will have this dt. So every time you pass that much dt, it will take a sample, and you pass dt again, it will take another sample. So that's basically what the whole sampling process is like. Okay, so every time you cross dt, you will take a sample. So in your waveform graph, you will have your dt or delta t, which is, it will contain, this waveform will actually contain 3 pieces of data: your delta t or dt, okay, and then you also need to know when you start sampling, which is your t0 or t0, and then you will also need an array of data, right? Okay, you need an array of data, let's say x0, x1. So if we plot x versus t, this is what we will get, and you go dot until x of n minus 1 for an n-sized array. Okay, n-sized array. Alright, this is an n-sized array. Okay, so this is an n-sized array. So that yeah, these are 3 pieces of important data that you'll need to describe, a periodic waveform. So we need a sampling frequency or a sampling interval, which is this dt. When did your time start? And how you need an n-sized array for if you are taking n samples. So these are the 3 basic data that is in a waveform. So this is what it looks like in Labview. Okay, a waveform is that what I was talking about just now. If you want to know what the components are, for example t0, which is the trigger time, or your t0 initial time, then you need your dt as well. It will give you the dt. You can actually extract all this data out using this waveform components function, so you can get your raw data. dt returns the time interval in seconds between data points in the waveform. So this gives you your sampling interval dt. Okay, just so you note, if you don't know that the audio sample or the periodic sampling frequency, if you don't know it's 44.1 kilohertz, you don't know what this waveform is, you can always check the dt, and you know that your sampling frequency is actually 1 over dt. Let me demonstrate in a little while. Okay, so and of course the last part is actually you have data values in that waveform, which is this Y matrix there. Okay, so that's more or less what the waveform data is about. So let me demonstrate what this waveform data is like. So okay, so if you want to get waveform data, right click your block diagram, go to waveform. Okay, I'll demonstrate again. Right click the block diagram, go to waveform, and you'll see this first VI or whatever, this function. It says get waveform components. Okay, it may differ as Labview, in later versions of Labview. I'm using the 2020 version. It may differ in like other newer versions, I don't know, but okay, you should be able to get something of that form over here. Okay, of course there are lots of other kind of waveforms as well, lots of other things you can do, but one very good one is to get the final time. That's very useful if you want to just get your final time value, so you can scale your plot accordingly. But that one I'll do that later. Let's get this basic thing done first. Alright, so you have this waveform value. If you input a waveform, it will output the Y values. But I want more than just that. I want the DT, and I want all the values. Okay, so how do you do that? So when you hover over this little box, okay, there will be one small little black dot at the bottom, and then you can just drag it down like so. Okay, you can drag it down like so, and then you can output Y, and you can output other attributes as well. So for example, you want to output DT, T0, and Y. How do you do it? You left click on one of these boxes. Okay, the first one I'll just type T0. Okay, second one I want to put it as DT. Okay, so same, anything that has the attributes function, you can just select. So click the T0, I can select T0, DT, or Y. So T0, DT, or Y, and the last one I will just want to select Y, and then I'll leave it as such. This is how you get data out of your waveforms. So I can actually wire this in. Okay, and actually over here something is wrong. This waveform will be broken. Okay, why is this such? Okay, says these two cannot be wired together because their data types do not match. So what's the data type here? Okay, the source type is a 1D array of waveform. So this wave reader file is actually giving a 1D waveform, but what data this little block here is expecting is a waveform. There's not a 1D array of waveform, it's just a waveform. So how do you actually solve this problem? So I'm not going to explain too much, but I'll just say that this index array actually helps a lot. You see this index array here, this index array function. Index array comes from right clicking, and you go to array, you go to this thing called index array. Now, I'm not going to explain now what that does, but I'll just say that I'll just say that it really helps a lot in converting the data into the correct type. So when I wire this in, this one actually works. So this is a rule of thumb for the audio, at least for the audio file. You can use this index array thing to actually get your waveform data. So alright, so how do I display all this data once I wire it in? Alright, so I can actually go here at T0, and then I can create an indicator. Okay, so T0 actually is over here. So this is where my when does my waveform start? Okay, and this actually shows like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, basically it's saying that t equals to 0 seconds, but that's a very long way of putting it. Okay, so what is my dt then? Okay, dt is the waveform sampling rate. Okay, I can create an indicator here. Okay, and then I can name this sampling time interval, because that's actually what it's doing. So, and then y will be, alright, y will be of course the values, right? Okay, so remember we had the n size array. The n size array in Labview is called y. So this is what the waveform data is about. So I can create a indicator here. Indicator will go maybe here, and this is my data values from waveform. Okay, of course, when the wires get messy, you can always what do you do this? Clean up wire. Okay, so it'll try to be as neat as possible, but I mean, you just gotta live with some of the wiring. Okay, so when I click run, I will see this. Okay, your waveform actually starts at time equals 0. Okay, on the date, okay, time is up. But my date, my month, and my year, they're not really indicated, so just ignore that. Okay, my sampling interval is 2.26. Okay, my sampling interval is 2.26757 times 10 to the minus 5. Okay, and if actually you take this value, alright, you take this value over here, I'll just paste it here. If you take this value and you take the reciprocal of this, you'll see that 1 over 2.27 ... etc. times 10 to the minus 5, you take the reciprocal, it becomes 44.1 kilohertz. Of course, with some decimal point corrections, but it is there to show you that this is your sampling frequency. So if you're not sure what the sampling frequency is, you can always use the get waveform data. Okay, and of course the data values from waveform are as you see here. These are all the relevant time dependent waveform values. So this is actually what this is showing on the graph here, except now this is shown in like I guess time equals in microseconds, like 20 microseconds, t equals 0. Then after the first one, after waiting this amount of time, then you sample the data. Wait this amount of time again, then you sample the data. Wait this amount of time again, and sample the data. So this is what this waveform components actually does. And you can see it's very helpful. It can help us to get an array out of this waveform data. It can tell us what the sampling time interval is, so that you can get the relevant frequency. Okay, so that's all I have for this video. So we went through the Nyquist frequency and working at least the waveform components stuff. Okay, so that's all I have. Thanks for watching.